Assalamualaikum warahmatullahi wabarakatuh, and welcome to our fourth chapter, which we will be discussing about induction machines. So this is the fourth topic, and for introduction to start to introduce you to induction machine, what we're going to do is that we're going to first discuss about rotating field, slip, and then understand the production of torque in this particular machine. So, in terms of content for this topic, we're going to start with a brief introduction to understand overall the importance of induction machine in application today. And then, secondly, we're going to look at, in order to understand basically the operating principle of induction machine, it is necessary to understand what is a rotating magnetic field. And in that particular matter, we are going to look at what we call as synchronous speed, which is the speed of that rotating magnetic field, and the air gap flux density that is produced by that rotating magnetic field. And then finally, next to that, what we're going to do is that from that magnetic field that is created by here, basically by the stator, we'll see later that as in any other machine, as in DC machine as well, we know that the torque is created due to the interaction between the field on the stator with a certain current on the rotor. So we're going to look at that part of torque production. And in order to look at the interaction between the stator and the rotor, we will briefly discuss about the rotor structure. There are two type of rotor structure that is available for induction machine, and then a particular notion that is specifically for induction machine, which is slip, are going to be discussed later on to basically understand the mechanism of torque production in induction machine. And then finally, we'll go through briefly discussing about the equivalent electrical circuit of the machine. Basically, the purpose of having an equivalent circuit is to be able to do an analysis, electrical analysis of the machine. For introduction, you have to know that induction machine is basically the most popular machine in application in electrical machine. 1/3 of electricity generated in the world. So imagine the whole electricity that's generated in the world. Basically, they are going to be transformed into a form of a utility that you can use later. So it is either transforming it into, for example, into lighting, transforming it into other form of energy, and mostly basically transform into mechanical or heat energy, right? And in transforming it into mechanical energy, basically 1/3 of electricity are transformed into mechanical energy, and most of them use basically induction machine to do that transformation from electrical energy to mechanical energy. So where do we use them? This mechanical energy that is transformed by induction machine, but they are usually used for routine and heavy application in industries, for driving machinery such as pumps, fans, compressors, conveyors, hoists, etc. So this kind of machine, basically, if you go into industries, into factories, you may find certain machines that have been working for 20 or 30 years without any problem. And most of the machines are induction machines, basically due to their reliability and ease of maintenance, as we will see later when we're discussing about the topology of the rotor. So historically, they are used for fixed speed applications. So they are what we call as started and operated directly by connecting to the supply of the building, right? So they will have basically a fixed speed used for fixed speed application. But nowadays we know that since the 80s and 90s, we have seen the increasing application of variable frequency inverter or variable frequency drive (VFD). There is development in terms of what we call as power electronics, and also speed control application. So we have seen induction machine used in other than fixed speed application as well. For example, such as in electric vehicle. So we know that electric vehicle is not a single speed fixed speed application. It is a dynamic speed application. So now we are able to control induction machine with a variable speed in variable speed application. So just like in DC motor, the principle of producing the principle basically the basic operating principle to produce torque lies behind the interaction between the stator field and the current in the rotor. So there is an axial current on the rotor somehow. We'll see how it is created later. And then there is a radial magnetic field. So radial magnetic field are created by the stator. So that is the similarity with a DC machine. So what is the main difference with DC machine, DC motor? So induction machine and DC machine, the main difference is that in DC machine, as we were talking about or speaking about the current on the rotor, in DC machine, the rotor current, which we call the armature current, if you remember, is delivered to the rotor via brush commutator, right? So you have to deliver the current to the rotor to make it operate, and then it is delivered to slip contact that we call a brush commutator, right? But in induction machine, the rotor, the current that they will have in the rotor is not sent to the rotor from the external mean, from an external mean. It is basically induced by electromagnetic action. So we don't supply current to the rotor. It is created through an electromagnetic interaction. It is what we call as induced. It is basically the application of Faraday and Lenz's law to create, to induce a certain current, a certain EMF, therefore current, in the rotor structure. So there is no mechanical contact. In principle, there is no mechanical contact needed to deliver current. So when I say no mechanical contact, it is for the purpose of delivering current, delivering power to the rotor. So the state winding produce therefore field excitation like in DC machine, but in this case it also supplies energy that's converted to mechanical output. So if you remember in DC machine, you may have a two separate supply where you have one supply to produce the field. So the field, the power supply that produces the field is just there to produce the field. It is not the energy that is produced by the field is not going to be converted into mechanical energy. It is only the energy that is going into the armature that is going to be converted into mechanical energy. But in induction machine, as we are not sending any energy into the rotor directly, it is the energy at the stator that is going to be converted into mechanical energy. So the stator winding produces both the field and the energy on the rotor that is going to be converted into mechanical output, right? So now we will begin to discuss about the field that is created in the stator. Okay, so the field that is created in the stator is not like in DC machine, which is a constant field where you have, for example, if you have a two poles machine, one gonna be north, one gonna be south, and then the flux, the magnetic flux or the field density is in a certain direction and it is fixed, right? But in AC machine, the field that's created by the stator is not fixed. It's going to rotate. It is a dynamic field that is going to move around and is changing throughout the operation of the machine. So it is what we call as rotating magnetic field, right? It's a rotating magnetic field, and it is that this rotating magnetic field is going to basically create induced EMF inside the rotor. So induction machine stator is usually supplied by AC current. Now we're going to look at how do we create create this rotating magnetic field. As we can see over here, basically you can see the arrows is pointing, basically is showing the intensity of the magnetic field and its direction. So it's a vector of the magnetic field. We can see that it is rotating. So how do you produce this rotating magnetic field? So it is produced by basically, we know that is an induction machine is an AC machine, alternating current machine. So it is supplied with AC current, and usually there are three phases machine. So it is a three phases machine supplied with AC current. So as we can see here in this graph over here, and in this graph over here, it's the same graph. So it's a graph that is showing the variation of the current versus time. Okay, so you have three phases. You have three AC current. Phase usually called phase A, phase B, and phase C, which are evenly distributed through a period of time. So what do you mean through a period of time? A period of time means if you take one single current, let's say this one, the blue one, phase A, when it completes one period, that's what we call one period of time, right? So across this one period of time of 2 pi, so one period is one rotation, right? 2 pi radian. Across this 2 pi radian or one rotation, we are going to place three current that are evenly distributed in terms of phase. Okay, so what you have is basically you have three current that are in delay that, with each other by 2 pi over 3, because one period is 2 pi divided by 3, you have 2 pi over 3. So we can see that we have current A sinusoidal over here, and 2 pi over 3 later you'll have phase B, current B, and 2 over 3 pi after phase B, you will see phase C in green. So that's what we mean having a three-phase current. I believe that you have all learned this in basic principle of electrical engineering when you are learning about AC analysis. So this is how an AC current three-phase are constituted. Okay, so what we do in induction machine is that we supply this current into the machine. So the machine will have basically multiple what we call as teeth or slot, where there will be windings, and there will be three phases of winding. And then the three phases winding may have basically each phase of winding have two poles, or what we call as the one pair of poles. So one pair means two poles, right? So you can see over here in the structure of the machine, this is the stator. You have A and A over here. So there are two teeth so this is what we call as teeth, right? Where you have winding that is roll around it, coils around it. So you have AA, you have B, and CC. So the winding of each phase are also mechanically evenly distributed. So for example, here we have two poles each with three phases. Therefore, we will have six poles, right? 6 poles mean we have 6 coils evenly distributed. So therefore, if it is evenly distributed, then the distance of each teeth are actually 2 pi divided by 6. Okay. So the interesting thing happened when we supply this coil with current of three phase A, B, and C. So the vectors that you're looking at over here, is the vectors that's representing the amplitude of the amplitude and direction, therefore, of each current A, B, and C. So for example, look at current A over here. Move to the right means it is in negative direction. Move to the left, it is in positive direction. So the variation of left to right is basically from maximum peak to minimum and then back to maximum. So it's the variation of current A. The same goes for current B. You can see the vector B. It goes from maximum to minimum or vice versa. C as well. And when we look at the vector, when we sum up the current, when we sum the vector, we do summation of the vector IA plus IB plus IC. We can literally see basically over here that it creates a vector that is rotating around the machine. Right? It is a vector that's rotating around the machine. So we can see it rotates like this direction, right? So when we sum up the current, the vectors, it creates an equivalent one current that is rotating. Therefore, what happens is that it's going to produce also a magnetic field. So you know that the current, when you have current, then you have a magnetic field around it. It creates an equivalent magnetic field that is around that current that is also rotating. So on the figure that you have on right side over here, it's basically the plotting of the current. So the two figure doesn't come from the same machine. So you can see that basically the arrangement of ABC are not the same. Here ABC is arranged in this direction, in the direction of counterclockwise. But here it is arranged in the opposite direction, is arranged in the clockwise direction. So if you look at the vector here, so this one is rotating in clockwise direction. This one is rotating in counterclockwise direction. So if you change, for example, the arrangement of ABC inversely, what happens is just that the direction of the rotating magnetic field is going to change. So we can see that as the current moves, as the currents go through its period, as the frequency with a certain frequency, there is a certain magnetic field that is rotating. So we have inside the machine, the stator creates a rotating magnetic field. What do we do with this rotating magnetic field? So what we are interested in is basically the interaction between the magnetic field, stator magnetic field, and the rotor. Therefore, we are going to look now the interaction with the rotor. So in previous slide, what we have looked is basically it's only the magnetic field created by the stator, but there was no rotor in the middle inside the machine. So if you put a rotor, we know that a rotor is also made of a ferromagnetic material. Therefore, the flux that's created by the stator, we would want to cross into the rotor to complete its magnetic circle, right? We have a very thin, a very small distance of air gap. Therefore, there would be no problem for the flux to go cross the air gap and make a pattern of magnetic field that is just like as shown over here. So this is an example of a four-pole motor that we are looking at over here. It's different from what we have seen just now. It was a two-poles motor. So now we have a four-poles motor. The variation of the radial and air gap flux density with respect to distance around the stator for a time from 0 to t/2 can be plotted as in the figure over here. So let me explain. So what we have over here is basically we are going to observe the variation of the magnetic flux of the flux density across the air gap as the machine rotates. So what we're going to do is basically uh, not as the machine rotates, as the current progress, right? We know the current is an AC current, it has a certain frequency, so it will vary across time, right? So what we want to look at is basically we want to observe how does the magnetic flux in the air gap look like as currents are moving. Okay, so what do we have here is basically in x-axis over here is the distance of the air gap in the air gap. So imagine we're starting over here and then we complete the rotation. So we start from 0 degree until 360 degrees. So this is basically the mechanical position inside the air gap. Okay, what about this axis y over here? So we can see this axis of y over here representing times from 0 to t/2, period over 2. So this represents the period, the time across which the current will vary, will change, right? So the period t over here, so I put a note over here. Period or time t is related to the period of AC current supply. So it's also called as the electrical period. It's t, or sometimes known as TE or TLX. So it is the electrical period. Okay, so it is the electrical period. So t/2 means half of the period. So half of the period, if you convert it into radian, it is basically it's pi. Whether in mechanical over here what we are observing is basically as the current moves, what happens is we can see that the flux pattern, magnetic flux pattern, also moves. So now it is over here when time equals to 0, but at times t equals to quarter. So t equals to quarter. The magnetic field from here has moved here, and then it has moved to the time. The electrical period moves to half, and then it moves again from here to here and then to here. Right. So we can see that the magnetic flux is moving because it is a rotating magnetic field. And if you look at the if you are plotting the magnetic flux density inside the air gap, what we observe is basically the form is sinusoidal. So the magnetic flux across the air gap are sinusoidal. And then we can see, what we can see is basically we can see two periods. So here, one period over here, peak to peak, one period, and then another peak to peak, two periods. Across all time, we can always observe two periods, so two north and two south. So two north and two south that represent basically four poles. So after half of the period, electrical period, half of the period, which is pi, right? In terms of electrical time, we had when we look at the, for example, look at the peak of the north over here, it has moved to here, which is 90 degrees. 90 degrees is basically pi over 4, but period over 2 is pi over is pi, right? I'm sorry, I mean so it moved from 0 to 90. 90 degrees is pi over 4, 90 degrees pi over 2. So mechanically, the flux in the air gap has moved by pi over 2 when the electrical period has moved by pi over by pi. I'm sorry, because half a period is pi. When the electrical current has moved by pi, the mechanical rotation of the magnetic flux in the air gap has only moved by pi over 2. So the mechanical rotation of the magnetic flux is basically half of the mechanical of the electrical rotation. Okay, so there is this relation of half. So where does this half come from? So basically the half is coming from the number of pair poles. We have 4 poles. It means we have 2 pair poles. So if we have 2 pair poles, it means the speed of rotation in mechanical is going to be divided by 2 in comparison to the speed of rotation of the electrical period. Okay, so it means that if the supply frequency is 50 hertz, then the rotating field speed is half of it, is 25 hertz. So if the supply or electrical frequency is 50 hertz, then the mechanical frequency will be 25 hertz. So what do I mean by mechanical frequency? Mechanical frequency means frequency of that rotating magnetic field. Electrical frequency is the frequency of the current. Mechanical frequency is the frequency of the rotating magnetic field. Okay, so mechanical, why I call it mechanical, because it is basically the speed that will be interacting with the rotor. It is not really mechanical speed. The proper term is usually is the speed what we call as the synchronous speed. So it is the synchronous speed. It is the speed of the magnetic field inside the air gap. So this synchronous speed is annotated as NS for speed synchronous, and it can be calculated by this formula: 120 multiplied by the frequency divided by number of poles. So the 120 is basically coming from the conversion of frequency into RPM, and then of course there is also the multiplication of the multiplication by 2 to take into consideration the pair, right? So one pole is basically 2 poles is one pair, so that's where this 120 comes from. So it's basically 60 times 2 It's basically 60 times 2. Okay, so if we want to calculate the synchronous speed, which is the speed of the rotating magnetic field, this is the formula. The speed of the rotating magnetic field, or what we call as synchronous speed. So this, I will be using the terms synchronous speed. Synchronous speed equals to 120 multiplied by F divided by the number of poles. So here the poles, we have 4 poles. So the consequence of that is basically we can basically for any type of machine, we understand that the synchronous speed depends on these two things. First is the frequency of the supply. Secondly is the number of poles. Therefore, we can predict the steady state speed of any machine if it is supplied with different AC current frequency. So usually there are two usual current supply frequencies globally. There are 50 hertz like in our country or 60 hertz in others that produce therefore different synchronous speed. So this is a table that shows you the usual number of poles combination with the frequency, therefore producing a different speed. So for example, the same machine that has 2 poles, if you use it in Malaysia and directly branch it or connect it to the wall supply, then you will be producing 3,003 kilohertz of I'm sorry, not 3 kilohertz, 3,000 RPM of rotation. 50 hertz produce 3,000 RPM. But if you are connecting it to, for example, another country that has 60 hertz system, then it will producing 3,600 RPM. So if you increase the number of poles, you can see that the machine will be reduced in terms of speed. Okay, so if you increase the number of poles because it's divided by P, it is inversely proportional to the number of poles. If you divide it by P, then the speed will decrease. But as the speed decrease, it is like so there is a ratio. If the speed decrease, then the torque will increase. So it's always like that. It is like the gearing ratio. If you decrease the speed, then the torque will increase, or if you increase the speed, then the torque will be decreasing. So that is true for the same for a motor with an equivalent rated power. So we have looked at the what we call as synchronous speed, but as in any vector quantity, a vectorial quantity, rotating magnetic field has also two components, which is the first one is the direction of the speed, and then the next thing, the other component of vectorial quantity is the intensity or the magnitude. So the synchronous speed shows the speed or the direction in which it rotates. But now we're going to discuss also about very briefly on the magnitude or the intensity of those what we call as flux wave. The term flux wave, sometimes we may see this of flux wave. Basically, the term is used because the form of the air gap flux density looks like a wave. So you might find this term of flux wave as well. That's why I am introducing it to you over here. So if we call the voltage per phase as voltage V, and the current that's passing through it as the current IM. So M over here, basically the subscript M's means magnetizing or flux producing current, because it is what it is. So imagine if you have one phase like this, you have a voltage V that you supply to the phase, and then you have a current circulating in it. So R is the resistance of that coil. So it's going to be very, very small usually. What's going to happen is that we know that if we go back into one, the magnitude of the flux density, or here we call it a flux wave, is proportional to the winding MMF, right? So B, the flux density is proportional to the winding MMF. Therefore, it is also proportional to the current IM, because MMF is the number of turns multiplied by current IM. Therefore, B is proportional to the current as well. But here, what we want to look is basically, we are not going to look into the current, because what interests us is basically the relation of the flux density or flux to the voltage and frequency. Because in induction machine, we are not going to be able to control the current because the current is going to be depending on the load. But what we are going to be able to control is basically the voltage supply. So there are two components of voltage supply that we can control. First is the amplitude of that voltage, and secondly the frequency of that voltage. So here we are going to try to deduce what is the relation between V and the voltage with the voltage and frequency. So when an alternating voltage V is applied, so if it is an alternating voltage, we will create an alternating back EMF, right? So in any coil, it is an inductor. So if you put a voltage across it, what's going to happen is you are going to get a back EMF. So here back EMF is induced in that state winding as well. So it can be modeled for a phase just like this, just like in your DC armature, DC machine armature, supplying with V. Therefore, you have in counter direction, in opposite direction, the back EMF. Okay, so from this what we call as equivalent circuit of one phase, we can write therefore an equation like this, right? So using your KVL, the voltage supply equals to so the product of the voltage across the resistor, which is IM multiplied by R, plus the back EMF. And in an operating machine, usually the voltage, just like in DC machine, if it is properly operating without too much load, what's going to happen is that the voltage is going to be more or less equals to the back EMF, right? We supply voltage, it's going to the magnetic field is going to rotate. If there is no load yet, then the back EMF is going to be very close to the voltage. So if it's going to be very close to the voltage, then we can also write that the following. Why? Because the back EMF is proportional to the exact flux density BM and frequency. So the back EMF over here that is produced is proportional to the frequency. So it's a property that is going to take into account. We're going to acknowledge. So the back EMF E is proportional to the frequency and the flux density. BM. So therefore, if the back EMF is proportional to this, then knowing that the back EMF is more or less equals to is very close to the voltage V. Therefore, we can say that the voltage V is also proportional to the magnetic flux density Bm and frequency. So we can therefore write Bm or the flux density of flux wave in the air gap equals to a certain coefficient K multiplied by V over F. So it is proportional to the voltage supplied, but it is inversely proportional to the frequency of the supply. So what is K? K is a parameter that's depending on the topology of the machine. So it depends on the number of turns per coil and depends on the number of coils, number of turns per coil. For example, in one slot, in one phase, how many turns do you have? And then how many coils do you have across the machine per phase? And then what is the coil distribution? So basically there are different types of coil distribution. So we are not going to discuss into that details for the moment in this particular subject. It's going to be the subject for advanced electrical machine design. But what we have to know is that if we have a coefficient K, so the magnetic flux density Bm inside the air gap or flux of wave is proportional to V over F. So this is an interesting property because it shows that if you want to control the flux density inside the air gap, therefore the strength of the magnetic field and therefore the torque, you can modify V over F. So there is in fact a control, what we call a scalar control, where you control the ratio of V V over F, right? So if you are only changing V and maintaining F, then you will change the intensity without changing the speed, because the synchronous speed depends on the frequency. Therefore, you will be able to maintain the speed, but you will be able to control the somehow the top of the machine. Okay. So now that we have seen the what we call as the rotating magnetic field, looking at its just now we were looking at its amplitude, its magnitude, and its speed, which is the synchronous speed. So now we are going to try to understand how does the torque produce inside the machine from that rotating magnetic field. So in order to understand that, we have to understand first the structure of the rotor, the design of the rotor. Okay, so in terms of rotor, basically there are two types of rotating induction machine. The most employed and the easiest in its easiest form is what we call a squirrel cage rotor. So this figure over here shows the squirrel cage rotor. So what is a squirrel cage rotor? Squirrel cage rotor consists of basically bars in aluminium or copper that are then short circuited on both sides. So at the front you have a ring, at the behind you have a ring, and you short circuit all the bars, making it and turning it into a short circuited conductor, right? And then what you do is basically you put a lamination. So this is basically a lamination. So it's a thin, it's very thin metal sheet that is stamped and then stacked together. And what we're going to do is that we're going to put this cage inside this lamination. So what is the purpose of this lamination? So the purpose of this lamination is basically to increase the flux density around the rotor structure. So what's going to happen later, as you can probably guess, there will be current that is circulating inside what we call as cage over here. There will be current that is generated and circulating inside this cage, and therefore there will be a flux, magnetic flux around it, and we add this lamination to basically to intensify and to properly conduct those flux to increase the strength of the flux, right? And in this particular rotor, squirrel cage rotor, there are no electrical connection to the rotor. So we are not supplying any current. So it's just this rotor structure put on the shaft. There are no conductors that's connected to the bar over here to create any connection electrically. So the current that is going to be circulating inside the cage is purely created through induction. So what do you mean created through induction? It means that you remember on the outside you will have the stator. The stator have a rotating magnetic field, and that rotating magnetic field, when it cut across the conductor, what's going to happen is that you recall the Faraday or Lenz law, you have variation of magnetic flux across this structure. So what happens is going to create an induced EMF. So in induced EMF across the rotor will create a certain current, therefore will be current created, what we call as induced current inside the rotor. So when you have an induced current inside the rotor, that current is going to produce in return a certain magnetic field around the rotor structure. So there is no external control over the resistance of the rotor circuit. So this is the rotor circuit. It is only bars. The resistance of the rotor circuit will be depending on the material that it's made of. There will be no mean to control or to change the value of the resistance. And this rotor is very popular. Most of the machines use this rotor because it's very cheap to manufacture. Therefore, the price of the machine is very low. And then secondly, there is another structure, what we call as wound or slip ring rotor. Wound rotor means it has winding, as you can see. So it is not made of bars, but the conductors is made just like in your DC machine armature. It is made of basically windings of coils, and it is basically connected to what we call as slip ring. Slip ring is just like your brush and commutator, but the purpose is not to deliver current into the slip ring, because the slip ring, the current inside the slip ring is also generated through the induced current. So the current is induced just like in the cage rotor. So what is the purpose of this slip ring? The purpose of this slip ring is basically there are three slip rings, so three slip rings for the three different phases, and the three slip rings is basically connected to a variable resistor. So variable resistor. So the purpose is that to allow us to change the value of resistance of the rotor. Okay. So the rotor in itself has a certain resistance of the coil, and that is connected to a certain variable resistor. So if we change the value of this resistor, we may change therefore the value of resistance of the rotor. So why do we need to change the value of the resistance of the rotor? We will see later in the control or starting of the machine. It gives us a certain interesting properties that will help us in controlling the machine. Okay, so it gives us a better controllability. So there is these two structure, either cage or wound rotor. Wound rotor is connected to resistor to control, to change the value of resistance of the rotor. But both of them, the current inside the rotor are generated by induced EMF from the rotating magnetic field. Having looked at the structure of the rotor, now we can discuss about what we call as slip. So this slip, SLIP, slip is the mechanism that produces the torque. So in order to understand the slip, we will look into two extreme rotor conditions. So we know that the rotor is in the middle of the stator, and that the rotor is the dynamic part that is going to rotate. So we're going to look at this the two extreme rotor condition with the stator field considered having the rotating magnetic field at a synchronous speed ns. So imagine you have so there is no depiction of the rotor. What we have here is only the magnetic flux or magnetic field line that is created by the stator. There's no depiction of the stator. I'm sorry. It's only the field line that's created by the stator, and it is rotating. Imagine it is rotating at a synchronous speed. So synchronous speed depending on frequency and the number of poles of that machine. So what are the two conditions? Imagine that if you have a synchronous speed around, but your rotor is stationary. It's not like this. The rotor is not moving. The rotor is fixed, not moving, but the on the stator, the magnetic field is turning around. So if the stator rotating field is rotating with synchronous speed, but rotor is not moving, what's going to happen is that you can see that you have a magnetic field line, right? So the magnetic field line will cut across the conductor, which are copper bar or aluminum bar. It will cut across the rotor conductors. And we know that if a magnetic field cut across the conductor, therefore the conductor see a variation of flux dV over dt. So Lenz and Faraday law said if across a conductor you create a flux variation of dV over dt, then will produce an EMF. So if the stator field is rotating at synchronous speed and the rotor is not moving, you will have the maximum EMF possible. So you have a high EMF in the rotor conductor because you have maximum flux variation. So when you have a back EMF, which is EMF is a voltage, right? So in the rotor cage or rotor conductor, you have created a certain voltage. We knowing that the rotor is a conductor, and you have a certain voltage in it, and therefore there will be current circulating in that rotor. So that's what we call as induced current, and therefore, so what's going to happen is that when you have induced current, you will therefore have create in return around it a certain magnetic field of the rotor. Okay, so this magnetic field of the rotor will interact with the magnetic field of the stator. Therefore, we will start to rotate. Okay, so we'll start to rotate. So then it rotates. So what's going to happen is that of course you have the field magnetic field across the rotor is going to resemble the magnetic field of the stator because that's where it comes from. So the magnetic field of the rotor is going to try to catch up with the synchronous speed of the stator. So and then when it try to catch up, we'll arrive to the next condition, the next extreme condition where the rotor now has achieved the speed of synchronous speed. So imagine the rotor with its magnetic field created through the induced current now catching up and now rotates with the same speed. What's going to happen? So if it rotates at the same speed, so imagine stator and rotor, both of them rotating at the same speed. So if both of them is rotating at the same speed, then what's going to happen is that the magnetic flux that is created by the stator is going to be seen as fixed as well by the rotor, right? Because it is moving with it. So if it's moving along with it, then any magnetic flux that's coming from the stator is going to be seen as constant by the rotor. So if you have a constant magnetic field across the conductor, what's going to happen? Then you will not create an induced current. Because remember, the length of Faraday law said the induced back EMF or induced current is created when you have dphi over dt, the variation of flux. But if they move with the same speed, then there will be no flux that is cutting through the conductor. Then there no dphi over dt. Dphi over dt equals to 0, so back EMF equals to 0. Then there will be no current induced in the rotor. So the rotor field will disappear. So the field of the rotor will disappear. Okay. So here is basically the depiction of the rotor field that's created by the induced current. So this induced current should of course created by not shown over here, the what we call the stator magnetic field or the flux wave. Right. So for the machine to produce torque, so for the machine to operate, to produce torque, the rotor speed, so we're going to call the rotor speed as N, must be different from the synchronous speed of the stator field Ns. So the rotor speed need to be different from the synchronous speed in order to create that variation of flux inside the conductor. So the difference between this Ns and N, difference between synchronous speed and the rotor speed, mechanical speed, is known as slip. That's what we know as slip, and it is normalized as in this equation over here. So slip is synchronous speed minus the rotor speed divided by synchronous speed. So that is what we call as slip. So you need to have a certain slip in order to produce torque. If slip equals to 0, then you will have no torque at all because there will be no induced current inside the rotor. So what is the value of that torque? So that torque is basically equals to certain coefficient K multiplied by the flux density, the air gap magnetic flux density B, multiplied by IR, so I that is induced in the rotor, IR, cos phi cos phi R. So what is phi R? If you look at the graph over here, we have in clear line, the bigger one is the air gap flux density. So air gap flux density is the one that is created by the stator. And then in smaller dotted line over here, with a smaller amplitude but in the same phase, we have the rotor bar EMF. So this is the voltage EMF that is created inside the rotor bar through induced EMF by the by the flux density in the air gap. And then what you see over here, the smallest one is the rotor bar current. So you have EMF, a voltage inside a conductor, and therefore you produce a current. So you can see that the voltage and the current inside the rotor bar are not in phase. There is a lack of a phi R. So why do we have a lag over here, a phase shift? We have a phase shift because basically a rotor bar is also an inductor. If it is an inductor, you know that it has a certain impedance, and the impedance basically delay the current. An inductor delay the current, so it makes the current a bit behind it. Okay, so that's how we produce torque. In order to produce torque, we need to have slip, which means the speed of the rotor will always be lower than the synchronous speed of the stator. Now, understanding that, we can now look at the torque speed characteristic of the machine. So we know that the induced EMF in rotor is proportional to the slip, right? So the induced EMF is proportional to the slip. So if you have slip equals to 0, then slip equal to 0 means the speed of rotor and synchronous speed are equal, then you will not have EMF. If you have the slip equals to 1. 1 is a ratio, right? So 1, that means you have the highest possible amount of the difference between synchronous speed and rotor speed, or rotor equals to 0, then you have maximum EMF. So the next question that we would ask is, what is the relation between torque and slip? So what is the relation between torque and slip? So the graph over here shows, in x-axis you have two things is x-axis. The first one on top is the speed, the synchronous speed and s, and at the bottom it also shows basically the slip. So this is quite usual for the graph in induction machine to show both the synchronous speed and the slip. And you can see the slip is basically going from 0 at synchronous speed and 1 when it is at 0 speed, right? Because we know that the slip is maximum when the rotor is not moving, so ns equals to 0, and then the slip is 0 when the speed is equals to synchronous speed. Okay, so I repeat, the slip is 0, or the speed when the speed is at synchronous speed, but the slip is maximum when the speed is 0. Okay, so the graph, what happened is that we have two graphs. The first one is in clear line is the graph of torque, so it is here in percentage, and then we have the graph of current is also in percentage. Okay, so what is this percentage means? This percentage is basically it is normalized to the percentage of the full load. Okay, so the full load, when you look at 100 over here, 100 represents basically the 100% of torque of the machine when the machine is at full load. Full load means you put the load. So this is the torque. 100% represent the torque when it's driving the load. Okay, so and therefore also there will be the current also when it is driving that particular load. So it is normalized to that percentage with regard to the load. So we'll look at a few different points. Okay, so we look first at the general tendency, general pattern of the graph. So the graph of torque, you can see when the speed, the synchronous speed or the speed of the motor is starting, it is quite low, and then it keeps on increasing, and then until a certain maximum torque. So I'm sorry, the torque is at a certain level, which is quite low, that then increase to a certain maximum torque, and then after a certain slip that is closer to the synchronous speed, what's going to happen is that the torque is going to reduce until 0. So we know that the torque going to be 0 if you have 0 slip. So 0 slip means your rotational speed of the rotor equals to the synchronous speed. And in terms of current, if you are at maximum slip, then you have a maximum rotor current, right? That is understandable, because we have maximum slip means the maximum induced current, so you have maximum current. And as the slip reduce, the current will also reduce until 0 when you are at synchronous speed. No induced current anymore at synchronous speed. So at starting, when you start the machine, when we are starting the machine, of course, at starting the machine, you will have your rotor at times t equals to 0. It is stationary, not moving. Therefore, we have a maximum slip equals to 1. So at starting, you will be placed here. The slip is at maximum, s equal to 1. The machine start with a certain starting torque. So this is what we call a starting torque. And then when you start, of course, the rotor is going to catch up with the synchronous speed. Therefore, the slip is going to move towards the 0 direction, towards the 0. So what's going to happen? The torque will also move in this particular form until it tries to reach the point of synchronous speed. But if your machine is basically has a certain load, what's going to happen is that it will not be able to go until the synchronous speed. It will stop at certain place where it is the operating point, where the torque is equals to the torque is going to be equals to the load resistive torque. Okay, a load resistive torque. So, and then it will stop there. So this is the point of what we call as normal torque or low load torque. So at low load torque, so what do we mean by low? Low means it's not attaining the maximum torque yet. So at low load torque, what we have is that we have a pretty small slip. As you can see, the slip over here is very close to zero, but it's of course not zero because the speed is not synchronous speed. It is very close to zero. We have the slip that is very small. The speed of the rotor is very close to the synchronous speed. So the torque is very small. It increases and can be approximated as linear as long as the slip is small. Okay, so the increase of torque with regard to the speed over here can be considered as linear, because if you look at this curve over here in this side, it is more or less linear. So what does it mean? It means that we can consider that if the load increases, so if the load increases, the speed going to be reduced proportionally. It's going to be reduced proportionally in a linear way. So it is more or less like your DC machine, right? You remember your curve of DC machine. If you are operating at base speed, if you are operating at so the curve looks something like this. So if you're operating at base speed, then if you are operating at no load, then you are going to be placed at the base speed, and then as the load increase, the speed gonna be reduced gradually, but it follows a certain linear curve if it is supplied with certain voltage. So the same goes for induction machine, but it is only true for low load torque. So low load torque is basically the region where you can consider linearity, right? So if the load increases, what's going to happen is going to move throughout this surface over here. If the load decreases, then the speed can increase gradually and proportionally as well. But that is not the only portion of the operation of induction machine that we can use. Imagine now if the load increases. So if the load increases, so from 100%, let's say it increased up to 300%. What's going to happen is that the speed is going to reduce. The slip is going to increase, right? The slip is going to increase. The speed is going to reduce until it attains a certain maximum torque. So a certain maximum torque will be corresponding to a certain slip value, right? So the slip will increase, and the speed of the machine, as you can see, is going to be smaller and smaller compared to the synchronous speed. Speed going to be smaller and smaller until the motor reach its maximum torque. After that, what's going to happen? If the load keep on increasing beyond the maximum torque, then what's going to happen? Maximum torque deliverable by the machine. What's going to happen is going to fall into what we call as unstable region. So what is unstable region? So in DC machine, there are two regions. In operating of DC machines, there are two regions. This region is what we call as unstable region. This region is what we call as stable region. So there is a maximum torque, Tmax, that you have to know that you should not go beyond, so that your machine will not go into unstable region. So unstable regions mean what's going to happen is that the machine will completely stall, because if you increase more, the slip going to increase. What happens is that when you reach this maximum torque and this slip, when you increase the load torque, it will not be able to increase the torque. Therefore, what's going to happen? The slip is going to quickly goes towards zero, goes towards 1. The speed is going to be drastically reduced to 0. See, so the motor is going to what we call as a stall. The motor going to stall. It's going to stop instantly. Okay. So those are the top speed characteristic of induction machine, and they are very related to slip and synchronous speed. So that's all for this week. Our discussion, it's been 1 hour. I hope you have learned a lot on induction machine. It's not that difficult. The only thing that you need to understand is there is the notion of induced current inside the rotor, and that's the important notion of slip. Okay, and then here we look at the top speed characteristic of the machine, which is very particular, where you have a stable and unstable region. Okay, so thank you very much. Until see you again in the next lecture next week, where we are going to discuss on the other mode of operation of induction machine, such as generator and braking, and we also briefly discuss about the equivalent circuit of induction machine, electrical equivalent circuit that will allow us to analyze the electrical and mechanical parameter of the machine as it operates. So thank you very much. I'll see you next week. Thank you.